All right, let me see if the laser pointer works. Cool. Does clicking work? All right, there we go. So this is building embedded systems and keyboards with Rust. My name is Brian Schwind. I've been working with Rust for 8 years at this point, I guess. I started in 2015 when 1.0 came out. I just worked with it casually from that point, and I started working professionally with it from 2018 or so. I work at Tonari, as Rio mentioned. Here's me on the website. That's me. So this talk is about building a custom mechanical keyboard, writing the firmware in Rust, and then just sort of a general overview of embedded Rust. So in the summer of last year, my coworker Pablo invited me to go to a keyboard store in Akihabara called Yusha Kobo. How many people are familiar with this shop? Okay, decent number. It's pretty much the only mechanical keyboard shop in Japan that I'm aware of. And when he invited me, I was like, not really into mechanical keyboards at all. And I was just like, I don't know about this hobby. It looks kind of addictive. I know things can get very expensive. There's like some weird aspects to it, like graduation photos with keyboards. People like to take their keyboards out to nature and take photos of it. So I was like, I don't know. I have this keyboard on my laptop already, and I can type plenty fast on that. It hasn't really held me back as far as I'm aware. So what's really driving all that interest? What is it about this hobby that makes people do that? But anyway, I decided to go to the store, and they just have keyboards laying out everywhere for you to just type on. It's the weirdest shopping experience I've had, where everyone's just there, quiet, but they're all just going on the different keyboards and just being like, oh yeah, that one's good, or no, that one's bad. And everyone has different opinions on it too, so it's interesting seeing everyone go through that. So I tried a lot too, and I was like, okay, it's just a keyboard, whatever. But then I got to this one, and I was like, okay, this is actually pretty nice to type on. I like this one. I had no idea what ABS double shot Dolce Blue meant, or Gateron Oil King. Is anyone here familiar with any of that? One person. Yeah, so I was very confused. I didn't end up buying anything because I wanted to do a bit more research on that. I was having lunch with some of my friends that went there afterwards, and someone mentioned, you type on a keyboard 8 hours a day if you're a software developer. Might be good to have a good one with you to enjoy it. That was enough to convince me. So is anyone familiar with those terms, like I said, double shot or oil kings? Does anyone want to explain it? What is double shot?
Double shot is the way the print is done. You have two different plastics for the print, the one for the letter and the one for the cap.
Exactly.
I assume that it's King's switches.
Yep.
That are old, maybe?
Mm-hmm. Yeah, so it's just an injection mold for the keycaps, but there's two different types of plastic, and that way the legends never fade away because they're plastic instead of ink. Does anyone know what oil kings are? No. Yeah, they're it's just the name of a switch. There's hundreds of switches that are out there these days, apparently. So I went home too, and I realized that I already had a mechanical keyboard. I didn't know. I took the caps off of it, and I had these guys right here. I could have just bought these and put them in there and had that similar typing experience I liked. And maybe I should have stopped there, but I didn't. So I ended up going back to the store. I kept thinking about this keyboard, and I went back and I was typing on it, and it was still great. I still liked it. But the issue was that I found another one that was new that wasn't there the first time, and I liked that one even more. So I spent an hour going back and forth typing on both of these, being like, which one should I do? And my friends left at that point. It's just deciding, I want to buy one, but I don't know which one. This didn't have a price tag on it, so I asked the staff member, yeah, if I wanted to build this is just a sample, but if I wanted to build one like this, how much is it going to be? And he's like, well, there's a few different parts to it. You don't just buy a keyboard. You're going to need a case and a PCB. some stabilizers for the wider keys, like a spacebar, a top plate, the switches themselves, and maybe some keycaps, which can be very expensive depending on which ones you want to get. I've never spent that much on keycaps, but they can get up there for whatever reason. It's just injection molded plastic, but it gets expensive. So he was saying basically it's going to end up around $500, or maybe I should say 500 J dollars because the exchange rate is pretty bad right now. 50,000 yen basically. And I thought, like, that's a lot for a keyboard, especially when I don't really know that much about them. I don't think I can do it. And at the same time, I know how to make PCBs. I've made a few in the past, the printed circuit boards. I could just spend weeks of my own time and save hundreds of dollars. Why not? So that's what I ended up doing. This is the keyboard that I made, and a friend of mine put it outside in grass. It's not like a crazy layout or anything like that, but it was just something that mimics I use a MacBook, so like I'm used to that key layout, so I wanted something that was pretty similar to it. I realized when I type, I never use the right shift key because I'm a bad typist, so I just took that out. It freed up some space. And then you have like the little function key in the bottom left that MacBooks have as well. So nothing too crazy. It's called the Key Ripper. So we used to build a lot of PCs at Tonari, like just custom PCs, and you get all these stickers with them anytime you buy a CPU or anything. So you get like the Corsair, Razer, AMD stuff. And I like putting those on kitchen appliances. So this is a coffee grinder with a Threadripper sticker on it. So we called it the Bean Ripper. And I decided, like, if I ever make consumer products, I want it to be like something Ripper. I think that's a cool theme. So I ended up calling this the Key Ripper. And I guess because I took the shift key out, so like I ripped a key out. I don't know. And I decided too, if I'm going to build this, I want to try embedded Rust and use that for the firmware. So starting off making the keyboard, I started with the physical part of it, so the PCB, the printed circuit board. For that, I use KiCad 7, which it just had a release a few weeks ago. It's an open source PCB design tool, and it's very powerful. I'm not going to go over like how you make all this stuff in KiCad, but there's a YouTube channel called Phil's Lab, which goes over a lot of designing real practical things in KiCad, and it's just a great resource. This is where I learned pretty much everything that I learned for KiCad. So when you start, you have to define like the parts you're going to use up front, and the microcontroller is arguably like the most important part, especially now with chip shortages and everything. A couple years ago, the Raspberry Pi Foundation came out with this microcontroller called the RP2040. Got some good things going for it. It's cheaper than a single Moomin keycap that you saw in the previous slide. Basically, it's $1. It can run Rust. It's available. There's a lot of STM32 microcontrollers that you may have heard of that are like when people talk about embedded Rust, they say like that's a good one to buy. Like it has good support and everything, but they are not as available these days because of the chip shortage. This one also has plenty of I/O pins, which I'll talk about later. It's dual core, I guess. That's cool. And it has some interesting peripherals, which I'll also address later. So obviously, if you're making a keyboard, one of the main aspects of it is just buttons, and lots of them. If you're making an electronics project that had just one button, let's say, you can just hook it up directly to your microcontroller here. So this is sort of like a schematic, like block diagram of the actual chip itself. So you have all your pins, input and output pins around the edges here. And this is just like a logical representation of that. So if you want to connect one button to it, that's great. You put one pin on the GPIO there, and another one to ground, or another one to some voltage. And when you press it, you can see the voltage go high or go low. My keyboard has 75 keys, though, so you need to have a microcontroller that has 75 pins if you wanted to do the same thing. So we have to get around that somehow. And just if you Google that, essentially everyone will say, okay, just use a key matrix. So I'll explain a little bit about what a key matrix is. So you end up with using GPIO pins here for all of the rows and all of the columns here. And let's say you're pressing Command and Shift and R at the same time. So how do we detect that you pressed all those keys at the same time? Another fact is that keyboards, like often like the higher end ones, will run at like 1,000 hertz. So it's reporting key presses at like 1,000 times a second. So you have 1 millisecond basically to report all the keys here, which is actually not that bad for a microcontroller. So what you do, and what most key scanning logic does, is it goes through each column and it sets it high. So it sets like a voltage high. It waits a little bit, and then it reads each row to see if the voltage goes high or low. So in this case, like Shift was pressed, so the voltage like goes up through here, goes through the switch because it's pressed, goes down, row 4 is high. So we look at the intersection, like row 4 is high, and we're on column 0 right now, so that means like Shift is pressed. So we turn that one back down low, and then we go to the next column, turn that one on, nothing's pressed, so all the rows are 0. Same thing for column 2. We get to column 3, and yeah, the command key is pressed as well, so the current goes through there, row 5 goes high. You get the idea. So you just do that basically 1,000 times a second. And you have at the end of it sort of just a list, like a matrix of Booleans that say this key is pressed, this key is not pressed. Does anyone know why we have these diodes here? Is everyone familiar with what a diode does? In case you're not, the current basically can go one direction through a diode and not the other. So if I had current going from row 3, it wouldn't go up through this diode and back down. If you didn't have diodes, let's say, there are some issues that pop up. So if we hold down Shift and Z and W, just as an example on this keyboard, there's no diodes in this case. So you set column 0 high, same thing as before, and row 4 is high. But what I didn't show you in the last slide is that the entirety of row 4 is high here. So that means it's going back to the Z key, which is also pressed, so the current ends up flowing through there, and then this whole other column, column 2, is high now. And then we're also pressing key W here, so the same thing, the current flows through that. And row 2 goes high, but we're still on column 0, we think. So we end up detecting that tab is pressed, even though it's not. And this is called key ghosting, and that's why diodes are in the circuit. Here's a few pictures of diodes on various keyboards. This is the through-hole diode. People sometimes lay them out in a nice way at the top of their boards if they're making a custom one. If you hand wire it, same thing, you're still going to see diodes there. This is a really beautiful version of hand wiring, same thing. And this is my keyboard. I didn't want to do like hand wiring or anything, so I just paid a robot some money to put the diodes on the board by itself. And this is actual like Rust code in my firmware that actually just does that key scanning logic that we just talked about. So the fact that it can fit on a single slide is pretty nice. We just have this key scan struct, which holds a matrix of Booleans. And when we want to scan, what we pass in is the set of rows, which are just input pins. I'll go over more of these. There's a lot of stuff that I didn't show, like what I'm using or what crates it came from, but you'll see that in a sec. We have the list of column pins. These ones are mutable because we need to turn the columns high and low as well, so Rust models that in its type system. We need some way to delay because once we set the column high, we need to wait a little bit so the current propagates. And I'm going to skip over talking about debouncing, but that's a whole topic in itself. But if you just read through it, it mostly makes sense. There's a bit of like unwrapping stuff here and some iterators, but essentially, we have this matrix. They're all false, so that's all keys that aren't pressed. And we just go through each column here. We set it high. We wait a little bit. In this case, it's like 10 microseconds. And then we just go through each row. And if that row, that GPIO pin is high, we just set it to true in the matrix at that point. And then we set that column low, and we just continue on for each column in there. There's a debouncer in here that sort of filters some noise that you can get when you press keys, but that's not super important. At the end of it, you just have this matrix of booleans, and it tells you you have this many keys, and these ones were pressed. The fact that it can fit on a single slide is pretty satisfying, and the fact that it's like fairly readable overall in Rust code is I like it. So going back to KiCad, when you create anything, you have to sort of create a schematic, and this just tells you how everything is connected to each other. You just say like, this pin is connected over here doing this thing. Here's our matrix again in the middle. There's a USB-C connector here, but overall, you just define how everything's connected so that KiCad can help you out later. So you get that defined, and then it kind of just dumps you into the PCB editor, and here's your parts. You deal with it. And you end up with just like little lines that connect each thing. It's like, okay, this pad needs to connect to this guy over here, so get on that. And there are some like auto routing tools that are out there, but it's not particularly great. They can get you some other way there, but essentially this is a puzzle that you have to solve, and you place it on the board, define like the edges and where you want to put things, and wire them all up. So at the end of it, you end up with, if you're making a keyboard, hopefully something that looks like this. So this one is a two-layer board. So the red layer is just like the back side or the top side, and the blue layer is the back side. Just a few random pictures here. This is the USB-C connector with the USB data lines coming down. This is the RP2040 itself. So there's obviously like a lot of pins going out connecting to all the keys in that matrix. And there's this, it's hard to tell it's there, it's this little SPI flash thing, and that's actually where the firmware is stored. It's stored outside of the RP2040, so that's there as well. And yeah, once you can also see like the key matrix as well, like the red lines here are the rows, and the blue lines here are the columns. So at the end of it, KiCad lets you see like a 3D model of your keyboard, and you can just sort of obsessively stare at it and try to find problems with it. KiCad can also tell you when you have like design issues or anything like that, like you connected this to the wrong pin or blah, blah, blah. But essentially, you upload it to your PCB manufacturer and hope it works. There's obviously some tools to help you tell if it's going to work or not, but it takes a while to get PCBs made, more about the shipping potentially than the actual process of making it. So while we're waiting for that to get shipped, we can move on to the firmware. So test. Wow, the battery died right as I went to a different spot. All right.
Wait for it to turn green.
It's green. How does it sound? Cool. So Rust on embedded systems, there's not a huge difference between embedded Rust and normal Rust that you're used to. The main two are the fact that you don't have the standard library available, and you also declare this like no main attribute. You don't have a main function. You kind of still do, but it's not the same one that you're used to. You also have no memory allocation in most cases, no threads, networking, or file system operations, and your code is pretty much the only thing running on this chip, which is a pretty cool feeling. Compile times are also pretty quick overall without the standard library and a bunch of other stuff that you need to link. So just like a clean build of the full firmware is about 11 seconds, and then if you modify something and recompile, it's about 1 second. So that's one area of Rust where the compile times aren't too much of an issue, which is nice. What you do have instead of the standard library is the core library, which the standard library mostly uses to export all of this stuff. So you still have your primitive types like U8, I32, all of that. You can still work with string slices. And in some cases, you can even mutate these if you have like an and mute. I don't know how to say it. I don't know how to verbalize and mute. I call it mute. I don't know. You can still mutate these for certain things, but you don't have that general purpose like string type because that allocates memory. You also have access to arrays, iterators, result and option, time duration, and futures is kind of an interesting one because that sort of opens the door for async await code in your firmware. I actually haven't explored that too much, but I'm very interested in trying that out. And if you really want to, you can still get allocation in no standard Rust by like opting in to this alloc crate. It's sort of a built-in crate in Rust. You won't find it on crates.io, but if you say extern crate alloc, it'll be there. The only caveat is you have to provide your own memory allocator to do that. And if you do that, then, sorry, you get access to things like vec and box and string and all of that. But if you wanted to stay without a memory allocator, you can have things that are sort of similar to a vec or a string in various crates, one of which is called arrayvec. Basically, you just define a statically defined size. This was an example code from a project I worked on where we controlled both sides of this communication, and we knew that the serial message was never going to be greater than a certain amount. So we just have an array of bytes, basically, of that size. And that works. Otherwise, yeah, it's not super different from normal Rust. It looks pretty much the same. So now what I'm going to do is just walk through some of the code. Going to operate this one-handed. And overall, like, there's not a ton of code there. I'm obviously using libraries from crates.io, but that's another sort of positive point for Rust is that you don't have to implement everything yourself, and it's very easy to pull in things that help you do what you want to do. Oh yeah, yep. How's that looking? All right. So just like a normal Rust project, you have your cargo.toml and the various dependencies you might use. In this case, I'm using the RP2040, so there's some crates available for that. But pretty standard overall. There's a few extra files that you need to have for, like, depending on which chip you're using and everything. And most crates will have sort of a starter template or like some information on how to actually generate these files. So it's not super interesting, but it ends up being like a copy-paste sort of thing. So I'll click on each code file here. There's only like 6 different Rust files, just to give you an idea of overall how much code is in here, which is really not a lot. So that's like 60 lines there. This is just a USB descriptor, sort of just data. Same with this. This is just defining key codes associated with, their actual like byte value. The key mappings for the particular keyboard. So like this is like a matrix. So the very upper left key is escape, and I sort of like flipped this code on accident. So it's like escape and then F1, F2, blah, 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 going down this column. But you can change that if you wanted. There's the key scanning logic, which I showed you before. I showed you this function. Just a little bit more in here as well. And then the main file itself. So it's 250 lines of code. And that's it for the firmware overall. It's not a lot. So that's kind of a cool aspect of embedded Rust is, again, like obviously there's a lot of underlying code in these things that I'm using. But if you want to get a project off the ground and make something work, you can do it quite quickly. So I did actually write this firmware after I ordered the PCBs and was waiting for them to ship. So that was it was cool to go through this. So let's see. I can kind of are people interested in just like going through the code at a more like detailed level? How are people feeling overall? Yeah. Okay. I won't go through like line by line, like literally, but I'll try to touch on the interesting points here. There's a crate called deferred format made by, I believe, Ferris Systems. It's sort of a way to have print line debugging in your application, because obviously you don't have just like a console that you can log to like you normally would. But you get the same sort of macros that you would use like from the log crate, so like error and info and warn. And you can see me using that in various spots here. If I have time at the end, I'll try to demo some of this. If you hook up a debug probe to it, it can actually like stream these logs over that back into your terminal, and you can run your program and get the output immediately, which is really cool. There's a crate called embedded HAL, which HAL stands for hardware abstraction layer, and it's a set of traits that are not specific to any particular microcontroller, but are just sort of related to embedded programming in general. So it has various traits for things like this pin is an input pin and this pin is output. You should be able to read from an input pin, and you should be able to set the state for an output pin. It doesn't actually describe like how to do that electrically, but the underlying crates down here, like the RP2040 HAL one, will implement those traits. Benefit there is that you can write sort of generic code over those traits for a driver, for example, and you can port that to the RP2040, or you can put it on an Arduino of some sort, or an STM32, any of those microcontrollers. The driver that you wrote should work on those, assuming they implemented these traits. There's also an interesting crate called USB device, which I'm using to actually act as a keyboard, because keyboards are it's part of the HID, human interface device class for USB. USB device, the crate itself, is more generic over USB communication, and then they have separate USBD underscore crates for the various like classes that you might use. So there might be one for human interface devices, there might be one for mass storage devices. There's a few out there, essentially. I'm using the HID one for keyboards. You have your typical constants that you would use in any program. This is not super important, but it's important for this to work. There's a crate out there called RP2040 boot that gives you what's called a second stage bootloader, which sort of like loads after the first bootloader, and then it sort of prepares your code to be called and run properly. So you need to link that in order for your code to get called. Here's just like columns and rows for the keyboard matrix. The external, like you have a crystal hooked up to your microcontroller. It sort of tells you like what frequency the chip is actually running at, sort of an input. So you have to define that. Static mute is kind of a no-no in Rust overall. So there's going to be some unsafe involved in setting those properly. But I kind of need to do that, unfortunately. And then in the case of the firmware, I need to have a way to have like the latest state of the keyboard, like what keys are pressed, and we'll see where that's used later. So like I said before, going back to the top here, we have these two declarations, which is a dead giveaway that you're in embedded Rust in some way. There's no main and no standard library. So going back to the main code here, this is slightly different. This isn't your typical main function. If you'll notice, it returns this. Does anyone know what that type is called? The return type of main here? Never. Yeah, it's called the never type. And the compiler, it basically means this function will never return. And it's like, what things never return? The only thing I can think of off the top of my head is a loop that just loops forever. And indeed, if you go down to the very bottom here, there's just a loop with no breaks, no conditions or anything. If you were to try to do something else outside of here, like if I tried to log something, sorry, I'm typing with one hand. The compiler will actually say, you said you were not going to return anything, but you returned the unit type up here. I guess it only shows it down here. So, no, actually, that's actually just a warning. Maybe there's some other part of it, but essentially it should stop you from doing anything else outside after that loop. Okay. Anyway, this main function is pretty much the same as what you would use on the desktop. You just have to annotate it depending on what chip you're using. In this case, Cortex MRT, and you have the entry. You have to say that this is the entry function that runs. So once you get here, basically you're the only thing running at this point. So do what you want. In this case, well, most embedded firmware that you see will sort of start off by grabbing these peripherals, which I'll hopefully have time to talk about. Peripherals are sort of the thing on the chip that let you communicate with outside devices in some way. There's all kinds of different peripherals. A lot of this is sort of ceremony that gets copy-pasted between stuff. But you have to start your clocks and define like what frequency it's running at. It's kind of low-level stuff. And eventually we get to the point where we want to start using our pins to be able to talk to the keyboard matrix and read those values and set them high and low. Don't worry too much about there's so many acronyms in embedded programming, especially in the Rust crates here. So I'm not going to go through each one, but ultimately you end up with this resource where you can grab different pins out of it. So looking at like the RP2040, it had like 30 different pins that you can just do whatever you want with. You can set them high, set them low, read values from them. So we grab the pins that we want here for the number of rows, and same thing for the columns. One thing that's kind of cool about Rust in this case is if I tried to use the same pin twice, it would actually complain that one of these pins was already moved. So the ownership and borrowing aspects of Rust come through in the type system for the firmware here. And this is great because oftentimes, and I've definitely made this mistake a lot in C or other languages, just accidentally using the same pin twice. And most languages won't catch that. So the fact that Rust does is pretty cool. Moving on, we just get a delay kind of thing. This is like chip specific again, specific to the Cortex like ARM processor. Just a way for us to like kill time and wait for something to happen. This isn't super important. Neither is that. When the firmware starts up, we just go ahead and do an initial scan of all the keys, passing in those rows and columns. This is the scan function that I showed before. And at that point, we can set, we have this sort of global like mutex thing called keyboard report up here. And this isn't the normal like standard library mutex, of course, because we don't have the standard library. But there's a crate called critical section, which will give you primitives like that to be able to lock things, because you'll see later we're going to be accessing this multiple times from different places. So we go ahead and store that initial scan that we did in that mutex, and that's just so right when we connect to USB, we'll have something ready to report to the host, like if a key was pressed or not. But before we start USB, we can go ahead and do different things depending on what key was pressed. If you happen to hold escape, in this case, the scan 00, while it's starting up, we can go ahead and put the chip into bootloader mode if we wanted to put new firmware onto it. So that's an easy way for users to be able to like flash new firmware to their keyboard. Just plug it in while you're holding escape. If you messed up your firmware, obviously this wouldn't run anymore and you wouldn't be able to put it in bootloader mode. So it's always good to have an escape hatch. In this case, I have a separate button on the PCB itself that lets you do the same thing, essentially. Again, we have the info logs here, so we can hook up a debugger or this debug probe to get that information at that point. So you can be like, oh, okay, it printed out initializing USB, so we at least made it this far. There's a lot of USB ceremony kind of stuff. This is, anytime you use the USB device crate, you're going to see very similar stuff here. So not super interesting. But at this point, various devices, depending on what USB class you're implementing, you'll have different crates that you start initializing. So for us, it's a HID class. We're going to be reporting keyboard reports, and we're going to be running this number of times, or like at this rate, which is 1 millisecond. So we're going to be reporting keys 1,000 times a second. And I'm from the States, so I set the locale to US. At that point, you can create the sort of generic keyboard device itself, and this is where you get to say that you're a manufacturer, and you get to name your product, and you can give it whatever vendor ID you want for USB. If you're selling this product, maybe you should probably buy a vendor ID and a product ID and register it with USB.org. But if you're a hobbyist, you can pretty much use whatever you want. At that point, so we've initialized USB. There's a concept called interrupts. And how many people are familiar with interrupts or have heard of interrupts before? Okay, decent number. Once we initialize this USB device, we want to start getting interrupts, and that basically is the USB hardware telling us, hey, I have new data for you to read, or maybe I'm ready for data to be written to the USB bus. And I'll show you the interrupt function in a second here, but this code down here is what actually enables that interrupt. So if you look down here, this is an interrupt function which is running every time the USB module is saying, like, hey, something's ready. But we're also reading some things from that mutex and some these static mute variables that I had at the top here are now being read from that interrupt. So we don't want this. Oh, sorry, I'm on the wrong thing. We don't want. That was a bad thing to search for. We don't want this interrupt running and trying to use things from this mutex before we've initialized it, or using the USB device or the USB HID. So we have to set those up first, and that's where this bit of unsafety comes from, along with enabling the interrupt at all. And at that point, it's just a loop, and we just scan the keyboard, get all the keys, and again, we use that mutex to replace the old keyboard report with the new one, and then we just delay 1 second and do it all over again. And this just runs forever. Down in the USB interrupt here, we're grabbing these static mute variables, and USB device has a function called poll. You can pass in the different USB classes that you have. So if I had more than one, I can act as like a keyboard that also has mass storage or something like that. So I would also have like another mass storage class that's passed in here, and that'll do its thing as well when it gets polled. And at that point, we just grab the keyboard report and we push it to the USB HID class. So that'll say, okay, that's the latest report. Next time the USB device polls me, I'll go ahead and report what I got. We can also pull data from it. In this case, it didn't work on Mac OS unless I did pull it, even though I'm not doing anything with it. There's a few aspects in USB that I don't quite understand yet that I need to work through. And then if this device supports USB suspend, we can, if there's a certain key pressed as well, we can wake up the device. So like if your PC is sleeping and you press a key on it, it'll wake it up. And that's pretty much it. There's some debouncing code, which I'll skip that, but it basically makes your key presses more reliable. Outside of that, there's not a whole lot of other code. Is there anything particular that people would like to look at in more detail?
I'm kind of curious why you didn't debounce it in hardware, like a capacitor.
Right. Why didn't I debounce it in hardware? You can add capacitors next to the pins, and that can act as a similar debouncer. In that case, I wouldn't have to write the firmware for that. The answer, I guess, is I was kind of lazy in a way, and just didn't want to put a capacitor on each switch. It's pretty much as simple as that, I suppose.
Very reliable, the software?
Yeah, the software debouncing is decently reliable, I would say. I've not really run into too many issues with it. If you start trying to go like higher than 1,000 times a second, you're going to start seeing issues with it. So you kind of have to tune it a little bit. That's what this debounce milliseconds thing is here. So it's configurable how long you want to wait before another key press happens after you've already pressed it once. Any other parts of the code anyone's interested in looking at in more detail? If not, I have a few more slides that I can go through. And how are we doing on time? Got a few more minutes left, essentially. So going back to the RP2040, wow, I don't know if we'll have time to talk about this. I'll just show some pictures for now.
Multi-core SoC. I was curious if you, I mean, you're running on one core, but have you tried running on both?
Right, so the question is, have I tried running on 2 cores? Because this chip does have 2 cores on it. The answer is no, because
I'm not sure.
a keyboard doesn't necessarily need to, although I could have done the key scanning stuff on that core on its own.
More general question.
Yeah.
What's the state of?
So I looked at that recently, actually. Last time I looked, it wasn't supported in the crate that I was using, but now it is. And it looks similar to the standard thread API, where you spawn sort of a closure that runs. So you say like you have core 0 and core 1, and you say like something.core1.spawn, and you pass it a closure, and that's basically your code that's running on the other core. And embedded Rust also has channels of some sort. I don't know if it's built into the core library. I don't think it is. But there's like different methods of communication on embedded systems to talk between those 2 cores. Yeah, I should try that out. The dual core keyboard.
I'm very curious because without some middleware, that's a real thing in the butt.
Absolutely, yeah. It looks fairly ergonomic to use. So going to the hardware itself, you have this package and you have all these pins on it. If you take off that outer layer and you take off, like there's like a metal oxide layer or something like that, you end up with this die where all the actual circuitry is. And this is about 2 millimeters by 2 millimeters, which is just wild to me. Something like this can run Rust and you can buy it for $1, and there's just so much engineering that goes into it. You have these regular patterns here, which are like your RAM and memory, and then this purple area is where all the peripherals are and the different cores that you have and a few other things. I probably don't have time to talk about this, but hardware peripherals and understanding that aspect of it is sort of the core of how you interact with things in embedded programming. Peripherals are just circuitry that lets you talk different protocols or do different things depending on what it is. SPI lets you talk to like storage devices or send data at a high rate. PWM lets you do things with like servos or like LED fading, that kind of thing. The point of these though is that if you tried to do that on your CPU itself, you'd be spending all of your time making pins go high and low at certain patterns, and you wouldn't have any time left to run your application code. So these hardware peripherals exist for you to sort of talk to them and tell them like, hey, write this byte out, and then just ignore it, and they'll take care of the rest in the background. This is a high level, this is from the Embedded Rust book, and it's sort of a high level view of the different layers that you have in Rust. So at the very bottom, you have the microcontroller and its peripherals. On top of that, you have these peripheral access crates, which let you talk to those peripherals. And the way you talk to them is just by writing bits to memory in particular locations. I don't have enough time to talk about this, but it's sort of at the core of how you interact with peripherals. Rust thankfully has some tools to generate these crates for you. And at that point, you don't want to use it at that layer, so we also have this hardware abstraction layer, which sort of combines those peripheral like register reads and writes into actual like tangible, useful things, like turning on I don't know, or setting a GPIO pin to be an output pin instead of an input pin or something like that. Usually involves a few different pointer reads and writes. There's that hardware abstraction layer, embedded HAL crate that I talked about earlier, and that sort of is a platform-independent way to write drivers. You can also have board support crates on top of that, which is like specific to a particular board that you might have, and then you have your application code at the top, which is like the keyboard firmware that I wrote. Yeah, I think that I should probably stop here. It's about time.
That's a good stopping point.
Yeah.
I'll still come up and ask my stupid questions.
I'll
Unless
cycle
the audience has more questions. Paul?
How much memory do you have on your CPU?
How much memory is on the CPU? I think it's like 126K, something like that. I don't know it off the top of my head. It's more than enough for what I'm doing.
Have you thought of implementing extra features to your controller, like, I don't know, a keylogger or something?
Yeah, so have I thought about doing or implementing extra features onto the keyboard? And the answer is yes. I haven't done that on the hardware level, so I don't really have anything, but people often put like RGB LEDs on their keyboards or rotary encoders to like have a volume dial. You could hook up a screen to it that plays animations or something like that. So there's a lot of stuff you could do, and maybe future versions will have that.
So I have one question similar to this multi-threading and tasking stuff. So I know that, for example, ESP comes with an STD crate as well, and you can run like no STD or STD, you can choose.
Right.
And I'm wondering, what do you normally do in Rust for multi-threading? Do you use STD? Do you use something like FreeRTOS? Is there something else? Like, what is the recommended way to do it?
This is for the ESP32
In
chip?
general, just in Rust, what is the normal way to do it? Do you use STD, or do you use existing library like FreeRTOS, which is pretty popular in C++ language?
Is that for multitasking? So I missed
Multitasking, yeah.
multitasking. Okay. Yeah, I have a slide for that. Sorry, this is all the stuff I didn't get to. Yeah, here we go. So you saw my firmware is just a simple loop, essentially, and that's not really an operating system, or I guess you could say it's a trivial one. The embedded Rust community has a few different ones. These are the ones that I know of anyway. There is Arctic, which is probably the most interesting one, which it leans on Rust type system a lot, and you have different tasks that you can define and resources, and everything is sort of driven by interrupts on the controller, and it's very very power efficient and very efficient in general. I think if you tried to do the same thing in C, it'd be sort of a disaster without the compiler telling you where things are safe and where they're not. Embassy is another popular one I've heard of, which does have async await in it. I haven't tried that myself, so I don't know. And then there's a few others as well. There are bindings to FreeRTOS, like you mentioned. So you can use that. But basically, if you have a bigger project, like not just a keyboard, but tons of different tasks happening, maybe you're connected to the internet, doing all these different things, you want a way to coordinate those different tasks and communicate between them and like give priority to different things. And these different projects help you organize that more. But yeah, I haven't used any in particular yet.
I feel like this is where Rust might shine. Like, I noticed that you also had a bit of code that was really well managed by Rust, like GPIO. Like, this is something that could be quite annoying in C++.
Yeah, for sure. I think out of all of these, I would say Arctic, the one at the top, is the most interesting and rusty one. So I'd give that a try because, like I said, it leans on type safety and the borrow checker and lifetimes and all of that in order to assert that you're not accessing things that you shouldn't be.
Do you think you can make this interrupt section, interrupt function that you wrote less unsafe? Because I think the whole thing was unsafe, right?
Yeah. Could Arctic make my USB interrupt less safe or more safe? And the answer is yes. I want to try that out at some point. I just haven't had time yet. Any other questions? I have a few pictures. I'll just cycle through these as well. This is when the PCBs arrive. Just raise your hand if you have a question. There's the finished keyboard. The cool thing about this, when you get these, you can literally just plug it in, and the RP2040 has a bootloader, so it shows up as a mass storage device. So you just plug it into your computer, and it just shows up as a little drive on your desktop. And you can just drag and drop firmware onto it from that point. Or you can go into the project and just do cargo run with release flags, and that's it. It flashes it and everything, assuming you have these other two tools installed, which is not bad. Sorry, one more time.
Like how challenging it can be to add Bluetooth, like to communicate with your host computer with Bluetooth.
Right, with Bluetooth. If I wanted to add Bluetooth support, I would probably go with the ESP32 chip, which does have Bluetooth and Wi-Fi. And there is Rust support slowly being added to it by this, just like one guy who was doing it in his free time. He got hired by the company that makes ESP32. So that's rapidly becoming a viable target for Rust as well. So I guess you wouldn't want to use like an ESP32 and an RP2040 both. So I would just write my application code just for the ESP32, use its Bluetooth radio, and have a wireless keyboard at that point. There's some benefits of embedded Rust. You can read those.
I have a question. When I was a little kid, I got a lot of kicks out of programming, like making a program that would make the LEDs flash on these old keyboards in random ways. If you wanted to modify your keyboard to have these LEDs and make it programmable, like how would you go about it?
Right. So how would I? So right now, I went the cheap route and made my PCB a 2-layer board, and that makes it a little harder to route traces around because if you run into another trace, you have to go down to the bottom layer and then go back up again. Once you add RGB LEDs to it, let's say, it's not a lot more traces, but it is a decent number going to every single key potentially. You could maybe route it on a 2-layer board, but I might switch to a 4-layer board at that point to make routing easier. And it depends on the LED that you'd want to use. Like if it's just a simple LED, 2 pins where you just send current through it, you might have some code to do that. But most people want RGB LEDs when they have these keyboards, and that involves. It depends on the LED again, but there's different protocols you can use. You could use the SPI peripheral on your microcontroller, for example, to send out data at the sort of pattern and rate that it expects and light them up. I've done another project actually at Tonari that does that, but it was only like 4 LEDs, but the concept is the same. So I have 10 or so extra pins on the board that I'm not using, and I could use those for LEDs for sure. And there's a lot of Rust crates as well that let you interact with those LEDs, already written with the embedded HAL traits implemented.
Gotcha. Actually, what I meant is these old keyboards had 3 LEDs in total.
Like
scroll lock, caps lock,
those
and
ones. Yeah. Those are the state of those LEDs are reported back to the keyboard from the host. So in that code that we were looking at the very bottom here, this pull raw output. There's a version of this call which is not just raw output, but an actual struct, which gives you back some information from the host, including which LEDs are lit up. So actually flickering the LEDs and all that is still technically like a host side thing, although you could just write some code in here to flicker the LEDs yourself anyway.
Gotcha. I did not know that. That's pretty cool.
Sorry, I gave you way too much information on the wrong topic.
It was still interesting, nevertheless.
That's good to hear.
Yeah. Great presentation. This is also the perfect segue into my questions. So you're obviously very comfortable on both the hardware and the software side. What's your background originally in?
Just computer science, and I was interested in video games like a lot of people are that get into computer science. So I started sort of trying to do game dev stuff, and I went to school just for computer science. I started getting into electronics in around 2016 when I moved to Tokyo, and I wanted to control my air conditioner. And so I made a PCB with an ESP32 on it to be able to send infrared signals to the air conditioner, and I'd be able to turn it on when I come home so the apartment's nice and warm in the winter before I arrive. And that sort of got me started on that. That was writing C at the time for that. But yeah, it ends up being a lot of fun having that thing that you can hold in your hands and just use. And it's very different from just writing pure software, just being able to see that physical output of what you worked on.
So you said you've been using Rust since 2015?
Yes.
Right?
Yep.
Damn, you have 1 year you're beating me with.
Yeah. Yeah, like I said, or I told you before, I dipped into it a few times, and sort of each time I went into Rust, the Rust language had gotten a little bit better, but starting off in 2015, you would probably run into a lot more like borrow checker issues, and it wasn't quite as nice of a language, so over the years it got better, and I became more determined, and started using it professionally around 2018. Everything before that, though, was just toy stuff at that point.
If there's one feature that was like really difficult for you to understand or master, what would be it?
I think I would have to say, like a lot of people say, lifetimes, but not just like understanding them, but trying to make your code follow that. So when I first heard about Rust and everything, it's like, oh, zero cost abstractions and like the most efficient code possible. And it's like, well, okay, you need to use references then. You don't want to copy memory and have lifetimes everywhere. So I was writing code that had lifetimes just scattered everywhere because it was just so infectious. And I was always like dismayed, I guess, that my cleverly designed code didn't end up working after like I added lifetimes to every single struct somewhere, and it just like all falls apart. So like getting over that and just learning like sometimes it's okay to just clone some memory and you know, get the thing done. It took a while to realize that.
How did you originally get into computers and deciding to study computer science?
So yeah, I played a lot of video games when I was a kid, still do. And let's see. I mean, my dad was an engineer and he had like DOS machines and stuff like that. So I'd play like Prince of Persia and whatever kind of stuff. I don't even remember how I like learned how to start up those games or anything on like a DOS console, but kids just find a way. They have infinite time. So I was always interested in that, and you know, just kept playing games. And eventually in high school, I took some computer science classes and wanted to try game development. And it was just like, yeah, I kind of got into it with graphics and that sort of thing, but never produced a full like fledged game or anything like that. Yeah, the video games is the short answer.
That's awesome. Prince of Persia is actually one of my favorites from when I was a little kid.
It's a beautiful game. The animation on that for the time is incredible. Everyone go play Prince of Persia if you've never played it before on MS-DOS.
That's correct. Anyway, great presentation. Thank you so much.
Thank you.
I hope you all enjoyed. And the pizza is here. Please feel free to grab a slice or two. There's also free beer in the back, so enjoy that responsibly. And my apologies in advance, but I'll have to be out of here around 8:30. So please help me just wrap up and sort of leave this place in good working order. And the next time you hold something like any little gadget, like a mic like this or a clicker over there, just remember that there must be a tiny little computer in there and somebody programmed that. Thank you for coming.
Thanks, everyone.
Have a great night.